I'm going to start in about 5 minutes. I'll chat to you then. Cool. Should we get started now?
Yeah.
Cool. We just started. All right. All right, cool. We'll get started now. One second. Oh, there we go. All right. Hi, everyone. Welcome to the second episode of the webinar series. My name is Leah. I will be your moderator. I will be your host for today. Behind the scenes, we've got Alicia as our moderator. And we've got a very special guest joining us today, Professor Arthur Lowery. How are you today, Arthur?
Very well, thank you.
Thank you so much for joining us today. We're so glad to have you join us. So before we get started with the questions, why don't you introduce yourself to the audience? Just tell us a little bit about what you do and stuff like that.
I'm a professor at Monash in electrical engineering. I am an electronic systems engineer, so I put together complex things. I work in optical communications as one of my main things. I had a company that developed software for designing optical communication systems that's used around the world, both for research and teaching. And I joined Monash about 14 years ago. And about 10 years ago, we started the bionic eye project at Monash University, which I'm here to talk about today.
Yeah. Awesome. So the first question that we've got to you is just sort of like how you got started on your journey. So what led you down the path of bionic vision? Specifically, was there anyone in your life that you found that like needed this technology? Or did you have someone that inspired you to pursue this sort of career path?
Good question. I always say that when I was very young, like 6 or 7, my grandma couldn't see very well. So one of my early projects was a system to read out menus to her so she could cook.
Yeah.
Of course, this was very primitive, and it was actually a box for dates, a wooden box, so the cocktails stick in it, and a wrapped up bit of paper and a light bulb. But my father said, "Oh, you probably need more than that in the box." And I think, given today's technology, you could actually achieve it because you would have a sort of text-to-speech processor, or no, you would just have a mobile phone, of course.
Yeah.
But no, the bionic eye more recently was when Kevin Rudd was in power. He had a Vision 2020 summit where lots of famous people got together, plus some engineers, and decided on bionic vision being a good thing to do after the cochlear experience. So we put in for some of the money there and saw it as a systems problem that you have a camera linked to a processor, linked to a wireless link going through the skull, and then going into some little tiles in the brain that send electrical impulses into the head. And your brain perceives those as flashes of light. So that's how that got going about 10 years ago. And we were fortunate to be able to drag together lots of people, or pull together. They were very interested, actually. So from different disciplines, physiologists, medics, mechanical engineers, electrical engineers, software engineers, that sort of thing.
Awesome, and that segues quite well to our next question about that. It was, what was your process behind designing and developing the bionic eye? Like, obviously, with something like this, there would be a lot of, like human-centered design around that. Was there like any interfacing that you had to do with people that experience blindness, and were there like things that you learned with those sorts of experiences that you didn't know before?
Yeah. Well, you're somewhat constrained by how you can send signals to the brain. So
Yeah.
some people send them through the retina if you have a viable optic nerve. Our approach was to go into the brain. So the sort of actual connection to the nervous system is fairly well defined. But what you can do is put software on the vision processor, because you start off with a very sophisticated camera nowadays. It's actually quite hard to get a cheap camera. So you end up with millions of pixels, and you've got to boil these down into something useful, such as a picture. And this is where we had the more interactions with people from Vision Australia, for example, who said what they might need in a day-to-day situation. And I guess one of the unexpected things of that was meetings that people wanted to, in the old days, sit around a table and have a meeting. They wanted to see who was listening and who was likely to agree with them and who was bored and that sort of thing. So having a sort of meeting mode which replaced people's faces with emoticons was one of the things that we worked on in the early stages. So it's human driven, I suppose, because the need is a human need. And we were informed by people's experience, but in the end, we're quite constrained by how you can actually send signals to the brain.
Yeah. And with that, like what you were talking about before, you had a lot of constraints in terms of, what sort of things that you could send to the brain. But the next question is actually, has your team ever been inhibited in any sort of way by resource limitation? How is that overcome? So obviously you mentioned some of that before. Do you care to elaborate on that sort of thing?
Yeah, well, I could answer this in many ways, of course. I mean, for things to be successful, you need money. And the good thing about the Rudd government, it was very keen to invest in bionic vision. And we got a small portion of the money at Monash. But that was enough to pull people together and get people interested and work with industry partners. And that lasted about 5 years. And I think, it's rather presumptuous to get a bionic vision project working in 5 years, because, you have to go through lots of trials for safety and efficacy. So here we are 10 years later on the verge of that. But, it's then there was a gap, but we had some benefactors who were very generous, the Beesons and the Finkles, to support us. We shrunk down to quite a tiny team there, and the NHMRC has given us money for the clinical trials, which we haven't yet spent, and now we're applying for more money from the health minister as part of the MRFF Frontiers program, which is to fund really the commercialization of biomedical research, and also solve this problem that when you make something very complex, there's not many people in the world who actually know how to do various parts of it. So searching them out is one thing, but it's much better to have them on the doorstep. So it's like Silicon Valley, where you can go around the corner and there's someone who can make this, someone who can make that. It's much easier to put together an entire product.
Yeah. Of course. So like on the flip side of that, so obviously you started all of this stuff 10 years ago, and 10 years ago, we wouldn't have the same advances that we did in technology like we do now. Did you ever find that when you were first starting this project, you were sort of limited in terms of like expertise with people, or even sort of like the research that had already been done? And how did that affect your development of, the bionic eye? Was there any like
Mm.
extra research that you had to undergo, any sort of like trials that you had to do in order to like implement that sort of thing into your
Yeah, not as much as you'd think, really. So um, the thing that has advanced, of course, in 10 years is things like artificial intelligence, signal processing, and things like that. And as I say, the cameras. But that's actually made our problem worse because the more pixels you get out of a camera, the more hard it is to get them anywhere. So most cameras now are designed that they fit in a mobile phone, and there's a connection of a couple of centimeters to the processor. So if you want to get a signal, down to a processor in a pocket or a belt, that's actually quite a hard thing. So our early work on algorithms to detect faces and things hasn't really changed. A lot of the materials haven't really changed that we can work with, because you're limited to a certain number of materials that interface with the human body and don't cause a reaction. So there's a very limited number of metals and ceramics that you can use, and plastics as well. So actually, it's quite a slow-moving area in terms of changing technologies.
Yeah.
Not much else I can say about that, really.
Yeah, that's fair enough. That was kind of interesting what you're saying with the new cameras actually inhibiting some of the like sort of processes that you can send to the brain. Like, did you find that you were having to sort of like limit what sort of things you were sending to the brain? Like,
well, indeed, yes. So we have a number of tiles, and each tile is about a centimeter across. And we can put a few of them in the brain, and each one has 43 electrodes. So you're only putting a very small number of points into the brain, of which you're hoping it interprets that as a picture.
Yeah.
And there's sort of recent research which is saying, well, if you send them sequentially, sort of dot, 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 your brain is much better at joining that up than if you present them all at the same time. So there are advances like that, but actually much less information than you would expect, because very few people have presented pictures to the brain. Initially, it was done in about 1967. With some advanced at the time electrodes on the surface of the brain, all connected to wireless receivers under this person's scalp. So they sort of had the whole scalp taken off, and like a hairnet of wireless receivers, and on the top of it, a whole bunch of transmitters, like a old-fashioned 1950s hairdryer.
With the wire out of them,
And if you look at some of the patents from the 80s, people had huge video cameras on their head, like you see in European Vacation or something. Americans used to carry around the world. That sort of thing has shrunk a lot, and you can get a lot more electronics inside the head, so you can decode signals and you can error correct them, that sort of thing. So there are advances like that, but quite a slow thing, as I say, from the late 1960s. But only sporadically have people done such things. There was a guy called DeBell, who was in America, but he actually had to move to Portugal because the FDA drummed him out of America. And there's actually a person in Australia with one of his devices in, but unfortunately DeBell died, and and he never provided the computer to connect this thing up. But there were about 13 people with those.
Okay.
Mm.
Yeah.
So that was sort of the up to about late 90s. But then there's been a bit of a gap.
Yeah.
There's a company called Second Sight in America who did a retinal implant and put that in over 150 people. And have been more recently putting it onto the surface of the brain. But there's not a lot of information about that around.
Yeah. Yeah. That's really interesting. There's like there's a lot of things that you touched on that a lot of people might not have considered in terms of the limitations and stuff, especially with advances in new technology. So I'm actually going to move on to the next question, which is a little bit different from the bionic eye.
Oh, yes.
I know that you've got something to show us, which we're all very excited for. So,
well, maybe, yes.
Yeah, we know that you're a really, really big music fan, quite a talented musician. I can attest to that.
Well, so yes, and I'm not professional.
How have you used your engineering skills in combination with your passion for music? So I know that you have a couple of things that you've built, like synthesizers and homemade basses. Do you want to talk about that just a little bit?
Yeah, look, I guess initially what got me into electronics was I wanted to do automatic control of my model railway, and that was done with a thing called a uniselector, which is a big switch that every time you get a click, it goes round one.
Yeah.
And they used them in old telephone exchanges. And then I got into guitars and built a guitar when I was, I don't know, early teens, let's say. And then when I was 17, I built this one, which was a guitar synthesizer. This bit's missing now. But it's standard guitar, but all the frets are all wired to wires here.
Okay.
And the idea was that goes down to a box, and which is a synthesizer, and every time you press the string down, it creates a switch contact and creates the note.
Yeah.
And the thing about guitar synthesizers in those days was they used the normal output of the guitar, or at least of each string, and it took a while for the processor to work out what note was being played. So by the time the synthesizer came in, it was a bit late. So this was hey, let's just press the string down and send a message.
So it acts more like a controller than using the guitar output.
Yeah. So it's just it's just like a switch, really.
Yeah.
But that was quite good because it got me my first job at Rakel,
cool.
where we made radios and things.
Yeah.
Because it used the same chips as they were using in their radio system. So I was a shoe-in for the job there. But there's a lot of things in music which are echoed, let's say, in electronics. And of course, there's electronic music and things which we all know about. But things like the way you can break down a note into a series of harmonics, so that has the note you think you're playing, like the C.
Yeah.
Then there's the second harmonic, which is an octave up, and the third harmonic, and the fourth harmonic. And these add to the complexity or the timbre of the sound. And a lot of these ideas are actually in electronics, and I've been using them in communications as well. That I had a paper on a system based on chords. That I guess the more complex story there is in the old days, when you were young, you'd have one amplifier and all your friends would plug their guitars into it, and it would sound like a complete mess because the amplifier would sort of distort, and if it saw two frequencies, it would create other frequencies and more frequencies, and they'd all be not musical. But if you have an amplifier per instrument, so one for the bass guitar down at the bottom, and one for the rhythm guitar in the middle, and one for the lead guitar at the top, even though they all distort, they're all distorting musically. And this is one of the communications ideas, that you could send different messages by distorting each set of signals separately.
Yeah.
And if each set of signals lay on a chord, then you could unjumble them. And I did prophesy, or say in the recent paper, that maybe that's how we interpret music, that we first listen to the lower notes, and then we subtract them and all their distortions, revealing the middle, and then we subtract all that and we reveal the top. So we can break down a complex thing like a symphony orchestra,
Yeah.
the different instruments, by using the fact that each instrument produces a mathematically related sequence of tones.
Yeah.
Anyway, I've gone on too much about that, but no, there is a lot in common with music and electronics. The relationship between waveforms and notes is a very common one.
Yeah. So, did you have something that you wanted to demo?
Well, there's a synthesizer here that I built just for fun. This was 2 years ago. So, I know. I need to turn the computer around. I can actually swap cameras. Ha!
Going on.
Yes. So if there's still enough light. So, yeah, this is the synthesizer here. I called it That 70s synthesizer. It's based on a bit of a Moog synthesizer. And it's a sort of zenith of analog electronics, where you can make different notes with different circuits. And, making a note.
So you're controlling that using a MIDI controller right now?
Yeah, well, it's actually simpler than that. It's just a keyboard. Which puts out a voltage, and that turns into a note on the synthesizer, just a single note. But you can do all sorts of things with it to make it more. That's a resonant filter on it. And you can make those sort of drum sounds that they had in 70s disco music.
Yeah. Did you have any favorite musicians that use this style of music?
Look, I mean, a lot of people use synthesizers over the years, and I mean, Thomas Dolby was one of the pioneers of synthesizer music, and in fact, he had a Fairlight, which was invented by CMI Music in Australia, which was one of the first sampling synthesizers where you actually could record things. Like, he used to record blowing over a milk bottle top to get a sort of very breathy sort of sound that you can get with that sort of thing. So that was very good. I used to like Steve Hillage, who had a synthesizer guitar, so that's why I built one.
Yeah.
I think he gave up on it because it was too slow.
That's fair enough. Yeah, you'd imagine the latency while you're playing that. It's a bit tricky to come around, isn't it?
Sorry, say that again.
I would imagine like all of those old synthesizers that you had before, because you said that the signal took quite a while to travel down. They'd experience like a lot of latency from like when they hit the note to when you actually hear it.
On the guitar, yes. Yeah. Yes, so they sort of gave up and just used guitar effects boxes, which are the sort of later end of a synthesizer.
Yeah.
But it's nice because you can sort of get immediate satisfaction of building an electronic circuit, and it sounds like something, and you play around with it. This thing's brilliant because it's got a lot of control.
Yeah.
You're not searching through menus for a setting.
Yeah.
You can do it live. So I guess that's why people like them for dance music.
Yeah, definitely.
I don't know how we're doing for time, really.
I think we're doing quite good for time. We've got one more set question, and then we can move on to some live questions because I feel like a lot of the viewers might have a lot to ask you. So we'll move on to our last question,
Mm-hmm.
the last set question. So just to finish off, what advice would you give to students? So maybe biomed students and engineering students who want to start developing medical technology.
Yes, well, that would take quite a time. I think be very patient because it's going to take a long, long time.
Yeah.
You should be following formal processes, which do cost a lot of money. There's a lot of money goes into documentation and regulation.
Yeah.
So, and there's a lot of patents out there. Fortunately, a lot of them are expiring because people have great ideas, and they patent it like, oh, I'm going to put some electronics in a box and put it in a body. That's a patent. But by the time they've done it, it's sort of expired. So there is freedom to operate, but you should realize that most companies, when they get into an area, they don't wait for someone to have an idea. They just sit, say, 10 engineers in a room with 3 lawyers, and the engineers just say lots of stuff, which may or may not be sensible, and the lawyers write it down and patent it. So that gives a lot of coverage for them. But as I say, that tends to run out if they're not careful. So, you need money, you need connections, you need a sort of ecosystem, and that's what we're trying to create really with our next grant, is to have a company that people have ideas rather than reinventing the wheel or the packaging. In our case, they can say, hey, can you put this into a package that can go into a body and will last for 25 years or 50 years, which is a very hard ask, to make something that lasts that long. So there's certain sort of challenges which are worse than in communications. In communications, if you wanted to put a fiber optic link across the ocean to test it, you would heat it up a lot, and you could work out that will shorten its lifetime. So you can say, hey, if this thing lasts 2 years at 85 degrees C, it'll last 20 years at sea temperature.
Yeah.
But in biomed, you can't really do that. You can't put something in something and heat it up to 85 degrees, otherwise you'll cook it. And so, it turns out that when you're actually testing things, it really does take almost real time to have any confidence that they will work for a long time.
Yeah.
So it's a very, very challenging environment, especially sort of class 3 active implantables, which we're in. It's one thing putting a hip in, which is a lump of metal with some ceramic on it, and it's another thing putting something external. But it's really, really difficult. As I said to the health minister, it's like making a mobile phone, but making it that big, and then sticking it inside someone and hoping it never goes wrong. So, look, it's really challenging. So what you really have to do is assemble a group of people who have a whole set of complementary skills, who can work together, communicate, document, and work with the medics and the clinicians and the financiers. So, there's a bit of a barrier to entry, but we're trying to create an easier pathway for new people.
Yeah, awesome. Thanks for that. And I think, that's really what MYMI is all about as well, especially with like the MedTech sector. That's what we aim to do, to create that ecosystem with students so they're able to, start pioneering this sort of medical technology.
Yes.
So that's the end of our set questions. We're going to have some live questions come up on the screen from some of the viewers. And so the first question we've got here is, what do you hope to see in the future of medical technology?
Well,
quite a broad question, isn't
it? I hope they will repair me enough that I will never die. And everything that goes wrong with me will be fixable. But seriously, well, that was actually serious. It would be easier if things didn't take so long to develop. But I don't know whether that's ever really going to happen. How do you split your focus between research
Next
projects?
question's already come up.
No, teaching.
Yeah, you seem like quite a busy man. How do you do it all?
Yes. Well, it's all rather difficult now. We're all sort of walled in. That my lounge room has become my lecture theatre, and upstairs is the research lab, and the shed is where I make things. I think with being an academic, you can't really control when you think about something.
Yeah.
That when I worked in, say, the defence industry, you weren't allowed to take anything home, and you weren't allowed to discuss anything at home. So, there's a clear barrier at 5 o'clock. It stopped. Whereas as an academic and also working in startups, you're thinking all the time, and often the best ideas come. My friend used to say when you're in the shower that sometimes you wake up and go, that's the answer to this problem. So
kind of on the go all the time, yeah.
Yeah, you're thinking about it most of the time, and of course, as you pointed out, what I do overlaps a bit. That some of the ideas in that synthesizer are now in a research project in optical communication. So yes, it's you're always. I always, whatever you're doing, you're feeling guilty that you're not doing the other thing. I should be doing some teaching now. Or, I should be doing some admin. Or, the accounts or something.
Yeah. Cool. We've got another question coming up.
Looking back on my career, yes. Mm-hmm. Did I end up, or did I send up?
Did you end up where?
Serendipity. I suppose I'm at an age where you do a bit of reflection of why did I end up here?
Yeah.
And there were certain things. When I was young, I was interested in theatre and stage lighting and that sort of thing.
Yeah.
And that sort of introduced me to electronics and music, and but I sort of realised there wasn't going to be much money in that. So I wanted to be a roadie for Pink Floyd for quite a while. And then they split up. I got this job in Rakel, which is a very interesting company, and they had everything really. They made their own chips, they made circuits, they made actual radios. They did everything in almost little sheds in Reading, which was not a very interesting place, but it was an interesting company to work for. And then I worked for Marconi Radar Systems, and that was sort of interesting, putting big boxes together. And you'd work out that one division would make something and with a big plug on it, and the other division would make it. They'd plug them together and they wouldn't work because they didn't really talk to each other. And that was the idea of sort of systems engineering, which sort of comes through in music, that you have guitar effects boxes and you connect, a distortion box into a filter, into a wah-wah, into a piece of that sort of thing. And that sort of led into, I got into computer modeling of lasers, which was another thing which was like a guitar. A laser produces colors of light, just like a guitar string produces harmonics. And the trick is to try and sort of select one. And that led into a company called VPI Photonics that I founded. It was called lots of things: Virtual Photonics, VPI Systems, VPI Virtual. Anyway, and that made software which is really quick for designing lasers based on these algorithms, based on energy going backwards and forwards on guitar strings. And then I've been using that software to do communication systems. So have I ended up, it sort of seems that way, that all these things I was interested in various ways keep on coming back, into research ideas. So yes. Did I suppose when I was very young, I just wanted to make amplifiers, and I did that for a hobby. So. That one over there, actually, I was playing with, was built in 1978.
Oh, really?
So, yes.
Are you still working on that now as well, kind of upgrading it as you go?
Yeah, I got into valve amplifiers for a few years and perfected those, and I've got enough of those around the house now. It's all the same sort of thing. It's sort of putting stuff together that you don't know what it's going to do.
Yeah.
That's what I found with Lego. You sort of put stuff together, and as putting it together, you know it's going to be a house or a spaceship or something. Whereas if you put together things like synthesizers and bionic eyes and software with lots of components, you don't know what it's going to produce. And that's sort of what's, when I press the button, what note is it going to produce? So I think that's an exciting thing.
Yeah, definitely. That was awesome. I think we have time for one more question. So, Alicia, do you have one more question that you want to choose from the
What makes a good...
what makes a good PhD supervisor?
Well, I've had students that go on and work at Bell Labs and Google and places like that. And it's what makes a good PhD supervisor is a good student.
Of course,
However, answering it a little bit more seriously, I think it's good to have a supervisor who knows about an area and already has contacts in that area. A supervisor who writes in the top journals. A supervisor who's well funded, so you can buy things and make things, initially in the PhD, it tends to be the supervisor coming up with some of the ideas, because the supervisor knows the area more. But as the PhD goes on, it should be the student who has ideas. I've just employed a guy who's just submitted his thesis and already has 61 papers. So, he's obviously a good student, but also had a good supervisor working in a good ecosystem. So, it's a difficult thing. I mean, as a PhD student myself, I only saw my supervisor about 3 times. And I sort of just got on with it, really. But I think, however many years ago it was more easy to get original ideas, so optical communications was just starting off, computer modeling was just starting off, computers were really slow, so if you came up with a good algorithm, everyone loved you. So I think it's actually more difficult now, just as an individual, to start a project and go, yes, this is going to change the world. Occasionally it does happen, but it's perhaps better to join a group that's well funded.
Yeah.
And the reason I did computer modeling was I couldn't afford any real bits and pieces, you know.
Yeah.
So,
yeah. Would you say that your PhD supervisor was a good one?
Oh, look, he started me off. I mean, he said the first thing, I was already a lecturer, actually. So,
okay, yeah.
So the first thing he said was, you know, as you're giving lectures, you want your computer program to run, or even in those days, compile, because it took half an hour for it to compile. So you'd set it off compiling and go and give a lecture and come back and hope it had compiled. I think getting into numerical modeling at that stage was a very good suggestion. And I have a friend who's a professor at Liverpool who has a similar thing, that he was into defects into crystals, that you get these pairs of defects in a crystal where it's just like piling oranges on top of each other, that if you sort of go wrong, there's a line across the oranges. And his supervisor said, I wonder why those defects always occur in pairs. Now, of course, that's led on to a career in solar cells and those sort of things. So, you know, so often it's that good initial question that you know, may not sound all that helpful, but it is based on a lot of experience of the supervisor.
Yeah. Of course. Awesome. Thanks for that, Arthur. Well, yeah, you guys heard it here first. Pick a supervisor with lots of money and you can do
Well, yeah.
Well, it's not. Yeah, well, thank you so much for that, Arthur. I'm sure a lot of people listening to that would have taken your advice on. So that actually concludes the live viewer questions, and that's actually come to the end of our webinar. Thank you again for joining us today, Arthur. I've really loved having you. I know a lot of people were really looking forward to hearing what you had to say, and you know, I feel like we've got a lot of really insightful things from you. So thank you so much again for taking.
I don't know whether I should press the synthesizer.
Yeah, why not? Give us some exit music to go. Someone's actually asked when your EP was coming out, so I guess that's coming out soon, isn't it? But thank you. Yeah, thank you.
Don't have EPs anymore. Yeah. Cheers. Bye. Or maybe you do. I know.
No. Thank you so much. So we hope you guys enjoyed episode 2. To keep up with current MYMI information and for future events, make sure to follow us on social media and subscribe to our mailing list. Episode 3 is coming out very soon, so look forward to that. Thank you again for joining us today.
Thank you very much, Leah. Bye.
Thanks for joining us today. Bye, Arthur.